Hello chemists, this is Ms. Placino and you are watching Screencast 2.1 on the nature of light. Today we're going to be discussing the behavior of light, namely does it behave as a particle or as a wave. Today's lesson is really physicsy in nature and you're going to want to have a calculator with you so that we can go through the calculations together. Let's take a look at the do now. The year is 1915. What do scientists know about the structure of the atom? What are they most likely trying to figure out? Alright, so in the previous unit we talked a little bit about atomic history. And by 1915, let's write that down, we knew about the electrons. As far as they exist, J.J. Thomson had discovered them and knew that they were mobile. And then shortly after that discovery, Ernest Rutherford performed his gold foil experiment and he found the nucleus. And again, the nucleus is just that small, very dense, positively charged mass at the center of the atom. So by the time 1915 rolls around, scientists really come back to the idea of the electrons. Actually, a little bit before then, they started looking at the electrons. And they're trying to figure out where are the electrons, how do they behave in an atom, what's the arrangement look like, and that proves to be a very difficult and challenging task. This entire unit is really going to be focused on electron configuration, and you might be wondering, how can we spend an entire unit dedicated to the smallest piece of matter that you know about? And hopefully as this unit progresses, you'll see that the electron has a lot of really interesting, unique properties, and it has behavior unlike anything else you've ever seen. So that's what we're going to be focusing on this unit, and in order to do that, we need to get down to how light behaves. Light is a form of electromagnetic radiation, and light and all electromagnetic radiation is going to have a wavelength and a frequency. Whoops. And hopefully you read a little bit about those in the reading last night. This is the electromagnetic spectrum. Over here on the left, we see very short wavelengths and very high frequencies, and these are relatively dangerous. If you've ever been to the doctor for an x-ray, you know that, or hopefully, they're covering you with like a lead vest, so only the part of the body that needs to be x-rayed, say your arm, is exposed. On the opposite end of the spectrum, we have things like radio waves, which have very long wavelengths and, relatively speaking, low frequencies. These are much less dangerous to you. You're probably being hit with them right now, and you're more or less fine. There's a really narrow band kind of in the middle of the spectrum that humans are able to see, from about 380 to about 780 nanometers. A lot of times we're talking about wavelength in this unit. We're going to use the unit nanometers. Those are 1/1000th of a meter. We'll talk a little bit more about those later. Just to go back to some basic information about the wave, the top of the wave is called the crest. The bottom of the wave is called a trough. And if you measure from crest to crest or from trough to trough on two adjacent waves, you get what is known as wavelength. And wavelength, again, is just the distance from crest to crest. We talked a little bit about this in the last slide. We tend to use nanometers, but we'll see that it's also important to be able to convert back to meters. We'll talk about how to do that. If you take a look at your notes, it asks you to determine which wave has the longest wavelength. I'll mark it off on the other waves, just so that we have a point of comparison, but my guess is you can probably figure it out without me even doing this. Hopefully you recognize that wave A has the longest wavelength. We also have the frequency of the wave, and frequency is the number of waves that pass a given point per second, and the unit hertz is used. 1 hertz is equal to 1/seconds, or per seconds. So in this window of 1 second, we would count the number of waves that pass. You're also asked to determine which wave has the highest frequency. Again, you can count, but you can probably just look and size this up and see that wave C has the highest frequency. Finally, you're asked to explain the relationship between wavelength and frequency of a wave. Well, hopefully by looking at this, you can see that it is an inverse relationship. The longer the wavelength is, the lower the frequency. The shorter, or the smaller the wavelength is, the greater the frequency. And we can discuss this relationship and perform calculations using this formula, C equals lambda V. Sometimes you might see the V replaced with an F. This is what I tend to use in class. C is a constant. It's the speed of light, 3.00 times 10 to the 8th meter per second. Wavelength, as we just discussed, is in meters or nanometers. And frequency, we can use hertz or per second. They are one and the same. Just a couple quick things about wavelength. I've mentioned it a couple times now. You're going to tend to see wavelength in nanometers in this class, but if you look at your speed, it's in meters per second. If you don't convert from nanometers into meters, you're going to get really strange answers every single time you perform any calculations. So I want to show you a really quick, easy way to get from nanometers to meters. Let's say you have 622 nanometers, and you need to figure out meters. A nanometer is equal to 1/billionth of a meter. So nanometers are extremely small. If I take this 10 to the negative 9th and I basically replace the unit of nanometers, I can really quickly convert into nanometers. Into meters from nanometers. Why does that keep moving? Times 10 to the negative 9th meters. Now I know that that's not technically correct scientific notation. That coefficient should be between 1 and 10, but the calculator will do the rest for you. So you can just quickly swap that out. You don't have to worry about performing any extra calculations. Speaking of calculations, you want to be careful about how you enter things into your calculator. My guess is, especially if you have a graphing calculator, that if you were to enter the speed of light, you would write it something like 3.00 times 10 caret 8. If you ever have the calculator spit out scientific notation to you, it doesn't give it to you in that format. Instead, you'd see something that looks more like this. 3.00 capital E 8. Now, you might not know this, but you can actually make that capital E on your own. You don't have to type out the asterisk 10 caret 8. You can just hit a couple buttons, more specifically the second function button. It should be in the upper left-hand corner. And then you're going to hit the comma button. And if you look in the same color that the second function button is, you should see two little E's. So when you hit second and you press the comma, you'll get that E, and then you don't have to write times 10 to the caret. That will do that automatically for you. In this unit, we're going to be using scientific notation a lot to perform calculations, and it's really in your best interest to start entering things in your calculator using this E instead of typing out everything. If you do that, you're going to get the answer wrong almost every single time because order of operations will kick in, and instead of reading that as scientific notation, your calculator is going to read that as a bunch of mathematical functions to perform. To prevent this, in addition to using the capital E, you can put parentheses around everything, but in my opinion, that's just extra work. That's a lot of extra keys to press, and ultimately, if you forget, you're going to end up with screwy answers. So be very careful about using your calculator this unit. Speaking of calculators, let's go ahead and perform a calculation. This is practice problem 2 in your follow-along notes. What is the frequency of electromagnetic radiation having a wavelength of 555 nanometers? All right, well, I always want you to show your formula, so we're going to be using, didn't expect that to happen, C equals lambda V. C is the speed of light, that's a constant, 3.00 times, 8 times 10 to the 8th meters per second. We know the wavelength, it's 555 nanometers. Be careful, it's in nanometers, I need to get it into meters, so I'm just going to add 10 to the negative 9th, and that's going to convert me into meters. And finally, I'm trying to solve for the frequency. So go ahead, carefully plug that stuff into your calculator, let the calculator do the hard stuff, and hopefully you're coming up with about 5.41 times 10 to the 14th hertz. If you've got this 5.41 number correct, but you have something other than times 10 to the 14th, there's a good chance that the way you typed this into your calculator didn't work out so well. So be careful, use the capital E or use parentheses, surprise me, both of them will work. But again, if you're getting a really, or actually anything other than times 10 to the 14th, check how you entered it into your calculator. You've got the right idea, but you're just not carrying it out correctly the way you type it in. All right, so this is really representative of light behaving as a wave. And in the early 1900s, scientists are very comfortable with the behavior of light as a wave. They like this C equals lambda V formula. It explains most of the behavior they see. Unfortunately, the photoelectric effect really throws a wrench into the whole light behaves as a wave theory. All the photoelectric effect is the emission of electrons from metal when light shines on it. So scientists chose different colors of light, and different colors of light will have different wavelengths and different frequencies. And they noticed that as they shined these colors onto a piece of metal, certain wavelengths or certain frequencies were able to actually cause electrons from the metal to be ejected or to jump off or out of the metal. If light was always a wave, this 700 nanometers, the red light, would also be able to eject electrons if you increase the intensity. In other words, if you make the light brighter. But science has found that it is not a question of intensity, it really depends on frequency. So certain frequencies will eject electrons, other frequencies will not. And again, this really caused a problem with the light behaves only as a wave theory. If you're a little confused about what the photoelectric effect is, from the course website, you can actually get to another video that kind of explains it and demonstrates it, and hopefully that will clarify it for you. This gentleman, Max Planck, sometimes you'll hear it called Max Planck. Either one is fine with me. In 1900, he was able to make some suggestions about what was actually going on in the photoelectric effect. And he came to the conclusion that energy is quantized, not continuous. And again, this explains the photoelectric effect. Now you might be wondering, what does the word quantized mean? So I'm going to take just a minute and give you kind of an analogy using a ramp and a staircase. Probably don't need to be labeled, but I'll do it anyway. The ramp is representative of energy or light being continuous, where the staircase is representative of light or energy being quantized. My guess is you've stood on a ramp and on a staircase at some point in time. So I'm going to draw little people. It's possible for you to stand here on the ramp, or here on the ramp, or here on the ramp, or here on the ramp. Basically, anywhere along the ramp you can stand. That's the whole point of having a ramp instead of a staircase. You're constantly in contact, and there's no place you cannot be. A staircase, it's different. I can stand on the first step. I can stand on the third step. I can't kind of hover on the 1 point, or I guess in that case, the 2.5 step. That doesn't exist. It is not an occupiable space. You are not allowed to be there. If you try to stop at the 2.5 step, you're going to either fall altogether or hopefully just drop back down to the second step. So Max Planck is saying that energy looks more like a staircase than it does a ramp. We see energy being continuous because we're really, really big, and the steps of the staircase are very, very small. To make another analogy, if you rub your hand over a piece of paper, it feels like it's perfectly flat. But if you were to investigate and look at that paper under a very high-powered microscope, you'd see that it looks like a mountain range. There are peaks, there are valleys, it looks anything but flat. However, since you are so big, you cannot even perceive those the differences in heights. It kind of works the same way here. You can think about the staircase as being, or the steps on the staircase being so small that we as people can't see them. We feel the staircase and it feels like a ramp to us. However, if you are small, I mean really small, like the size of an electron small, you do see the steps and you see that there are rules about where you can and cannot exist. And that's going to have a really tremendous impact on the model of the atom. Since we no longer can explain the behavior of light only using C equals lambda V, we need to use another formula. And we're going to use E equals HV. So E is energy. We're going to see it in joules or kilojoules. H is Planck's constant. And you can think about it as being kind of like the height of each step. Times 10 to the negative 34th. That's telling you that this is an extremely small number. And hopefully that's something you would have guessed, since it's completely imperceivable to us as people. Hopefully you recognize that that needs to be a really small value. And just like in the last formula, V is going to be frequency in either hertz or 1/seconds. So let's go ahead and try a calculation using this formula. What is the energy of a photon of green light? And a photon is really just, you can think about it as a little packet of energy with a frequency of 5.76 times 10 to the 14th hertz or per seconds. As always, give me the formula you're using first. E equals HV. We're trying to find energy. We know Planck's constant, 6.626 times 10 to the negative 34th joule seconds. And again, you could kind of think of that as just being the size of each of these steps. We're going to multiply that by the frequency, 5.76. Ooh, what happened there? 6 times 10 to the 14th, 1 over seconds. Seconds times per seconds, that'll cancel out. And that's going to leave us with an answer in joules. Go ahead, punch that into your calculator, being careful about how you set up scientific notation. I know I'm repeating myself, but it's really important here. And you should come up with a final answer of 3.82 times 10 to the negative 19th joules. So a very small amount of energy that is required, that is required or produced from this photon. All right. So as a result of things like the photoelectric effect, scientists had to accept that light really has a dual nature. Namely, it can behave as a particle and as a wave. So we see primarily wave-like properties, but it is possible for us to think about it as a wave of particles. So really what I mean by that is we think about our wave. Maybe looks something like that. Wave of particles, maybe think of like a dotted line. So kind of the same general behavior with just the nuance that it can behave as a particle. And really whether it behaves as a particle or as a wave depends upon the situation. So this is where we're going to start with our study of the electron. I know that this can be kind of confusing for students to wrap their head around at first. Take a little bit of time and try to see if you can write a summary of today's lesson. And if you're really panicking about not being able to understand this stuff, don't stress. It is complicated and confusing, and not to be pessimistic, but it's going to get even more confusing as we continue. The behavior of the electron is really unique. At the very least, make sure you feel comfortable using those two different formulas and that you can perform calculations. All right, that's all we've got for today. Look forward to seeing you again soon.